All right, let's get right into it. Today we're tackling one of the biggest, most fundamental divides in all of chemistry: metals versus nonmetals, the ultimate showdown.
Seriously, just look around you right now. Everything you can see, everything you can touch, pretty much all of it can be sorted into one of these two giant categories. So what's the deal? What are the fundamental rules that make something a metal and something else, well, a nonmetal? Okay, so to kick things off, let's start with the basics, right? The stuff you can actually see and feel. We're talking about their physical properties. And this is where the differences really start to pop, or, not shine, depending on what we're looking at.
First thing you'll probably notice is luster. You know that shine, that glint you see on a piece of metal? That's what we're talking about. It's exactly why we love gold and silver for jewelry. They're super lustrous. Now, nonmetals? Totally the opposite. They've got this kind of dull, flat look. No shine at all.
Okay, next up is something called malleability. Sounds fancy, but it's basically the hammer test. It's this amazing ability metals have to be pounded into super thin sheets without just breaking. The perfect example, the aluminum foil sitting in your kitchen right now. That's a metal hammered crazy thin. Try doing that with a non-metal and you'll just get a pile of dust. They're brittle, they just shatter.
And right alongside that is ductility. This one's the wire test. It's the ability to be stretched out into a thin wire. This is like a total superstar property of metals. I mean, every single wire in your house is probably made of copper for exactly this reason. You're just not going to make a wire out of sulfur or, a gas like oxygen. It's just not going to happen.
And just to give you an idea of how wild this gets, check this out. Take just 1 gram of gold. That's about the weight of a paperclip, right? You can stretch that tiny amount into a wire that is 2 kilometers long. 2 kilometers! I mean, that's just mind-blowing. All right, so we've laid out some pretty clear rules, haven't we? Metals are shiny, strong, and you can shape them. Simple. But here's the thing about chemistry. Just when you think you've got it all figured out, you meet the exceptions, the rule breakers. Let's dive into the rebels of the periodic table.
So the general rule is metals are hard, right? We think of steel, of iron. You're not going to just bend a steel beam with your hands. They're tough, they're solid.
But then you get to these guys, the softies. Meet sodium, potassium, and lithium. These metals absolutely demolish that hard and tough rule. I'm talking so soft you can literally cut them with a knife. It's like slicing through a stick of cold butter. Seriously.
Okay, let's flip the script. What about nonmetals? The textbook rule is pretty straightforward. They are terrible conductors of electricity. They're insulators. That's it.
But say hello to graphite. Now, graphite is just a form of carbon, which is a nonmetal. It's the same stuff that's in the tip of your pencil. And yet, against all odds, it's an excellent conductor of electricity. It's so good, we actually use it to make electrodes, a complete and total rule breaker.
Okay, so physical properties are one thing. We know what they look and feel like, but what about how they act, how they react? This is where things get really exciting, even a little explosive. This is where we see their true chemical personalities.
So let me ask you this. Why are metals like sodium and potassium always stored under kerosene oil? I mean, you'll never just find a chunk of sodium sitting out in the open. It's always submerged. What's up with that? Why all the special treatment?
Well, here's why. These metals are so incredibly reactive, they'll actually have a violent reaction with the oxygen just floating around in the air. And this isn't a slow burn, it's what we call exothermic. It releases a ton of heat, so much heat that the metal just catches fire all on its own. So that kerosene oil, it's basically a bodyguard, creating a barrier that keeps the air away.
All right, let's zoom all the way in, down to the atomic level. So what happens when a classic metal comes face to face with a classic non-metal? You might think it's a battle, but it's really not. It's more like a negotiation, a powerful transaction based on giving and taking.
Let's take a perfect example: sodium and chlorine, the two atoms that team up to make your table salt. So you've got sodium, and it has this one lonely electron in its outer shell that it's just dying to get rid of. Then you have chlorine, a nonmetal, which has 7 outer electrons and is desperately searching for just one more to feel complete. I think you can see where this is headed.
And there it is, the great electron transfer. Sodium hands over its extra electron to chlorine. It's a done deal. Now, sodium, having lost a negative electron, becomes a positive ion, and chlorine, having gained one, becomes a negative ion. They both get what they wanted, a full outer shell, but now they have opposite charges.
And what happens when opposites attract? You get a bond. This powerful pull between the new positive metal ion and the negative nonmetal ion is what we call an ionic bond. And it's not a weak connection. It's the super strong electrostatic force that locks them together. They've just formed a brand new substance, sodium chloride.
This new partnership, this ionic bond, creates something completely different. The new compound has its own set of rules, it's on unique properties, and it's nothing like the original metal or non-metal that formed it. It's a total transformation. So let's check out what makes these ionic compounds so special.
Let's talk about conductivity again, because it gets really interesting here. If you take a solid salt crystal, those positive and negative ions are locked up tight in a crystal lattice. They can't move, so electricity can't flow. But if you melt that salt or dissolve it in water, you break that rigid structure. The ions are suddenly free to roam around, and once they can move, they can carry an electric charge. Pretty cool, right? And really, it all comes back to that super strong bond. As you can see here, that's why they're hard, crystalline solids. The ions are just held together so tightly. It's also why they have crazy high melting points. You need a ton of energy to break those powerful bonds. And their solubility in water? Well, water molecules are clever. They can get in between the positive and negative ions and pull them apart. So when a metal meets a non-metal, it's a story of giving and taking electrons, a complete transfer. But that's not the only way the story can go, which leads to a really big question. What happens when there's no metal around? What if two non-metals meet? They both want to take electrons. So what happens when, instead of transferring, they're forced to share? Well, that's a whole other kind of bond, and a story for another time.